Hello everyone, I'm Siddhant Singh and I'm again back with HDFS session. So I have already recorded one session where I have talked about what is big data engineering, and if you haven't seen that, you can go back and see that. So today we are going to discuss about HDFS and its Hadoop distributed file system, like what's its component and what's its architecture and like how it actually works. So yeah, we can begin with HDFS components. So yeah, it stands for Hadoop distributed file system, HDFS, and then we have Yarn, yet another resource negotiator. It actually provides all the resources. Then we have MapReduce. It's a programming based data processing. It is discovered by Yahoo, and then later it has been used in HDFS. Then we have Spark. It is in memory data processing. We will talk about this later in the our course. Then we have Big Hive, query based processing of data services. Then we have HBase, NoSQL database. Then we have Mahout, Spark, MLlib. This is machine learning algorithm libraries. For processing all the machine learning thing, we use this. Then we have Solar, searching and indexing. Then we have Zookeeper, which is managing our cluster. Cluster is basically all our resources, from where we are operating. And then we have Uzi. It is job scheduling, like which job we should be prioritized and which job should be processed first. According to that, we can schedule out the task. We can use Uzi. So I'm going to start with HDFS architecture. Now let's imagine a system where four nodes are there: node 1, node 2, node 3, node 4. So these nodes are given like this. So suppose this is a 500 MB, or this is 500 MB, 500 MB, 500 MB. Suppose you have divided this into four blocks. So now you want to store a data. So let's say we have here some information. This is some information about block 1. This is another information about block 2. This is another information about block 3, and this is another information about block 4. So let's suppose this information has 250 MB of data. So what we are going to do is we are going to store this information in some blocks. So the arrow that are pointing towards here is basically a block that is storing this information. So suppose this is 250 MB and this is 500 MB. So we are storing our information here in this particular blocks. So you can see this is how HDFS architecture basically works. We divide everything like here in a block system, and then we are storing information one by one like that in each other. So now to access this particular information, let's say you are a user and you wanted to access some information about block 3, which is stored in block 3, this in this particular block 3. This is basically data node 1, data node 2, data node 3, data node 4. So basically in data node 3 you have information about block 3, and now you are a user who wanted to access this particular information and want to perform some operations. So let's see how you can do that. So there is something called metadata. It looks like this is a file 1, and this is a block 1, and this is data node 1. So this is basically our file 1, block 1, and this is basically our data node 1. This is our data node 2, data node 3, data node 4. So it's look like that. It is a file 1, our block 1, and data node 1. So this particular file 1 is stored in particular block 1 in data node 1. So this, by this particular fashion, we have uh, prepared some kind of log of information, and that's what we call metadata. Metadata is basically holding those information. So basically this particular metadata is contained in this particular name node. This name node has this particular metadata. So what actually happened is basically, let's say we are here at client node. So we particular make a request here in name node, and name node has this particular metadata. So this metadata, what it gives back the information again to name node, and then in name node gives this metadata information to client node. Now when you come further here, you can see that this metadata gave information to name node gives the same information to client node, and client node now has all the information about all the blocks here. So you can see that to access the blocks information, like which file is where, we need to access it via metadata, and metadata is stored in name node. So this is how we basically hold the information in name node, and this is how we are going to access the information, and this is how we process the data. This is how we manage the data. Now in HDFS architecture, suppose one node is down, like let's say this particular data node is failed due to some reason, let's say some virus came or some calamity happened. Due to that, this particular node is destroyed. Now what's going to happen, like how can we get the information like which holds the data? So for that particular thing, we have something um, called replication factor. It is already sorted in HDFS architecture. So it's called replication factor. So it's basically replicate the information in other nodes also. So if one node goes down, we have this particular information in other nodes also. Let me show you what I mean by that. So let's say we have here by default replication factor 3. So let's say we have here file 1 is here, block 1, data node 1. So in data node 1 we can see there is b1, in data node 2 we have here is b2, and data node 4 we have here is b1. So you can see there are, we have at three places we have stored the b1 information. So you can see because the replication factor is 3, so for that we have stored the information at three places. So by doing this, why we are doing this, the reason for this is that if one node goes down, we can come down and we can look at like where that particular information is present. So this is very crucial to know, so that we have a fault based detection system, where if any problem happen, our system is genius enough, or it is designed in such a manner that fault doesn't cause the stoppage of operation. So this is very important, and it is one of the major mechanism in HDFS. Then there is another feature I wanted to show you, that is heartbeat system. Basically every data node has, it sends heartbeat in every 3 seconds. Every data node sends heartbeat in every 3 seconds to this particular name node, and if heartbeat is not received by 10 consecutive times, that means that data node is dead or it is not running properly. Now why we need this heartbeat basically is because we need to know that our data node is working properly. So we need to get some response in every 3 seconds, so that we know that okay, this particular node is fine. Let's say if we don't receive any heartbeat or any, or you can call a signal in every 3 seconds and for 10 consecutive times, then this means that this particular data node is been down and it's not been working. We have to come shift to this particular blocks. So it's very important feature of HDFS. This is how it works, like this is how it came to know, okay, this particular block is not working, this particular block is working. So yeah, so let's say if heartbeat if this particular data node is not sending heartbeat and it goes down, then the fault tolerance or replication factor comes down to 3. The reason it comes down to 3 is because it is set as a 3 by Hadoop admin, but now one of the data node is down. So because of that, now we have only two options, right? Because let's say B1 is present in only two nodes. Here you can look at it, at this data node and it's this data node. So now only two default replication is allowed in this particular architecture. So yeah, that is another important thing to know. And yeah, and it will also maintain the copy of data node. Like let's say this particular file is destroyed, this particular block is destroyed, so it creates another one, that is block B1, and it has like data node 3, data node 2, and data node 4. So it create another file size. It create basically another copy of data node. So this is also an important aspect, like metadata is also going to be create another replication copy. So yeah, let's discuss another thing, like what are the versions of Hadoop. So there are like three versions of Hadoop, and Hadoop 3.x is the latest version of Hadoop. So it's basically Hadoop 1 is released in 2011, 2 released in 2012, 3 released in 2017. So Hadoop 1 it introduced with MapReduce and HDFS, is to say MapReduce framework. It's used for processing the file, and management also. So it just only process the file, but to manage the resource better and to make it multi-tenancy, to make it multiple user, we have to introduce it with yarn. This yarn has to be introduced in 2012. So to we manage the resource very much better, and to allow it to use with multi-tenancy. Multi-tenancy means multiple user can use or access the resource. Now Hadoop 3, which is released in 2017, it provides more generalized support to user defined types, and it memorization or resource provider goes beyond its CPU and memory. For example, we can define our own GPU software license and all, and we can also use locally attached storage also. This is not possible in Hadoop 2, but now here it is possible. And we can also schedule the yarn tasks. Okay, and now the another difference is here support single tenancy only, but this support multiple tenancy in yarn, and here multiple support is of tenants is also allowed. Okay, Hadoop 1 is uses master slave architecture that consists of single master and multiple slaves. So in this case, master node get failed, then entire cluster becomes unavailable. So basically this, if this particular name node got failed, then whole data node will be destroyed in here. Like this is the like master node, this cannot get failed. So this need to be protected in Hadoop 1. But in Hadoop 2, what happens is it comes with multiple master. Like it has secondary name node, like like this has this it contains one multiple copy of name node, secondary name node. So what happened is, if this failed, this secondary name node will come into action and it handle all the processing of data. So yeah, it comes with that. And yeah, in Hadoop 3 basically it supports multiple name node, like it has more than two name nodes available. So like it's like super secure, like your data is not going anywhere if any of the nodes or name nodes or any of the data node is been destroyed. Okay, so another limitation in Hadoop 1.x is it is limited to 4,000 nodes per cluster, but here it has 10,000 node plus cluster in Hadoop 2, and here they like improved its scalability more, and it can have more than 10,000 nodes in one cluster. So yeah, in Hadoop 2, like manual intervention is needed for name node recovery, but in Hadoop 3, we don't need any manual intervention for name node recovery, like it happens automatically. In here, like Java 7 is minimum support, and in name node in Hadoop 3, Java 8 is the minimum support version. And so where are we? Wait. So yeah, it support HDFS default like and FTP, Amazon S3, Windows, Azure, storage flow file system. And in here, like in Hadoop 3, all file system included Microsoft Azure Data Lake file system is compatible with Hadoop 3. It uses 3x replication scheme that result in 2000% storage overhead. And Hadoop 3 uses eraser encoding in HDFS that helps to reduce storage overhead. It has 50% storage overhead. Basically, what happens is when we store some data into the machine, it basically, put some kind of burden on machine. But what happened in Hadoop 3 is it uses some kind of eraser encoding that helps to reduce the overhead burden. And now it added support for in Hadoop 3. It added support for GPU hardware that can be used to execute deep learning algorithm on Hadoop cluster. Basically, for deep learning thing, like it requires GPU to perform those advanced algorithms. For that particular thing, for GPU support, Hadoop 3 has the option. Hadoop 2 and Hadoop 1 doesn't come with GPU option basically. So yeah, now move forward and let's see the name node failure thing. So basically we have discussed it previous now. Let's discuss again. Let's say this particular name node which is being handling this particular data node, this particular name node got failed, and it has some metadata also. Now this metadata also got failed, so that means this particular name node failure causes we cannot access the metadata also. So this brought down the complete failure of the system. This particular thing happened in Hadoop 1, but in Hadoop version 2 this particular thing doesn't happen. What happened is there is a secondary name node which always maintains the copy of primary name node. So how it does that? Let's see that in next section. So basically there are in Hadoop 2 and Hadoop 3 there is two important metadata file. One is fs image and second is edit log. So basically let me for explanation purpose. So yeah, basically let's say for fs image, so let me explain you what is fs image. So basically let's say uh, we are seeing one football match, we are seeing one football match and Messi scored a goal against Real Madrid. So now what happened here is this particular information is being stored in fs image. So fs image basically stored this information at 5 minutes of play. So now goal, goal happened and fs image stored the information of the play. So now what happened is football match progressed, and at 20th minute what happened, Ronaldo scored a goal at 20th minute. Now what happened here is when he scored a goal we need to update the fs image, but how to update the FS image. Like to update the FS image, we need edit log. Now what edit logs does, it hold the information of previous FS image data. Now what happened is, we need edit log to see like what is the previous score. So now we can update the data in FS image, that is 1 at 20 minutes. So you understand now, like FS image and edit logs are like two important metadata files that we need to update the information, to update the data flowing in the machine. So yeah, it's like a snapshot of the file system at a particular time, transactional logs that changes in HDFS file system. So basically this particular FS image, like you know, wait here, this particular FS image where we check the previous score of the game, and in edit logs we check the like what is the previous score, and by that FS image and edit log we like merge that and we come up with 1 score. So like this we have like at one point we have FS image and at one point we have edit logs. When we merge it, we come with new FS image. That new FS image hold our current data, like what's the present status of that particular data. So yeah, now for name node recovery, we have here secondary name node which is passive at that particular time, and this particular name node is active at this particular time. So now here this name node give information to FS image and edit logs, and this particular FS image and this particular edit log send the information to SSN. Now this particular SSN, what it does, it merge this whole thing and it create new FS image. So it particularly, this particular SSN, as secondary net node, this particular thing knows like what's the status of the current data. So that's how we like check the whole thing, like what's going on inside the whole system. So let's come here. Now there's whole particular thing which I have explained, like this is a name node, this is a secondary name node which is passive, this is FS image, this is edit log, and name node sending information to FS image, it is sending information to name node, and this whole thing is sending information to SSN, merging it completely, and then new FS image is created. This whole thing happening for every 30 seconds. So this whole thing repeat at every 30 seconds, and that every 30 seconds thing is called checkpointing. So basically it performs this merging thing and updating new FS image. This whole process is called checkpointing. So this is how whole thing work in HDFS architecture. Now let's come here and let's discuss the scenario of failure, like what actually happened when failure happened. Let's say this particular name node got failed. Now this SSN become active because this got failed, and it starts going into memory. It starts using the memory of that particular name node. So this particular thing become operational, and it has the whole information of new FS image because it doesn't require its previous FS image or edit logs. So yeah, now let's discuss another scenario here. Now let's say new SSN comes into the picture, right? And the whole process now become active, right? Like previously it's happening in this name node, now this SSN become active. Now because this got failed, this becomes active. Now it's the responsibility of the Hadoop admin. Yeah, I'm an Hadoop admin. Now it's my responsibility to bring another name node in here, and I have to introduce this another name node here, and I have to make this new SSN is name node, and this name node that I have introduced, I have to make it passive. So basically I have to change the role of a particular name nodes. So this is how the whole thing works. Like the introduction of name node is very important. So you know because failure has happened and we need to replace the resources. To replace the resources we need to bring another name node and to make it active, and this new SSN has to make it passive, and then we have to merge it, and by merging it we have to make the operational available on this particular name node. So yeah, this is the how whole process is going to work. So let's I'm going to repeat again because I think it's a little bit more complicated. So let me repeat it again for you guys. Like, let's say this is a name node, this is FS image, this is edit log, and this is a secondary name node which is provided in Hadoop architecture for backup kind of thing. Let's say my laptop has a memory, and for backup I have to keep another memory. So let's say if my main memory got failed or something happened bad to my main machine, I can use my backup memory and I can perform my data operation there. So for this particular thing, let's say this failure happened here, this is an FS image, this is an edit log. It usually send information to secondary name node also. So now this will be passive, like in this video you see this is passive, like but after failure it becomes active and it uses in the memory. Like this machine goes out of the picture and this machine comes in the picture, and it uses new FS image and memory. Now what Hadoop admin needs to do is he needs to bring another name node to replace this particular name node. So this particular name node will be replaced with another name node, and the whole operation will be uh, presume again. So this new SSN will be then again become passive, and this become active, and this is like merging operation will begin and checkpointing again will happen. So yeah, this like whole process begin again. If you are confused about this, you can like go back to the video again and you can replay it again like that. So this whole concept is like super clear to you. Let's begin with another you know phenomena, or let I will call it replica in the architecture. Like let's discuss deeply like how replica is actually working in HDFS. So let's say in this architecture I have three location. One is Bangalore, one is Sydney, one is New York. So in Bangalore location we have data node 1, data node 2, data node 3. In Sydney location we have data node 4, data node 5, data node 6, and New York location we have data node 7, data node 8, data node 9. So now we have placed this data node in a rack at a certain location. So this replica we are going to use to if any failure happens we can access the data again. Let's say in data node 1 we have this particular information about blocks, and location 2 we have this information, in location 3 with this location. So what happened is basically to forward the information from one location to another location, it requires a huge amount of network bandwidth, and it required a lot of input and output operation. Let's say I'm here at Bangalore and I wanted to access the data from here, this particular thing, and now this is in Bangalore, this is in Sydney. Let's say this code failed and my backup is placed here in this particular location in Sydney. So now to access the data from here to here, from Bangalore to Sydney, it requires a lot of huge amount of network bandwidth, because this we are talking about very large amount of data, like millions of TB of data. So to access that amount of data, we required more input and output operation, and that becomes very difficult, very hard to execute at that point of time. So we are going to discuss like what are the scenarios and like how we can do this very efficiently, like because we need to design a system so that we can access the data very efficiently. That's, data engineering is all about using things very efficiently at a certain point of time. So yeah, so we, let's say we have a node here, like block here in a rack of data at location Bangalore. And what happens is, let's say in Bangalore location we have data node 1, data node 2, data node 3. So to access this, let's say failure happens here. Now I need to get this particular block information. It's stored here, the replica is stored here. It's very easy for me to get the access, to get this particular data at very a small amount of network. The reason is that it's present in Bangalore location only, right? So at the Bangalore location only. So for that reason, the block information is very less. The network amount required for this block information to access the data is very less, right? But let's say scenario, let's say because of some calamity or some earthquake happen or some electricity fall on that particular building or something happened, the whole server, whole data center got burst out. Now what's going to happen at this particular time? you know we are going to lose all our data, and this is a loss to a company because there is no replica available. And because we have stored all our information at single place, it's like we put all eggs in a single basket, and when something happened to that basket, all the eggs are fallen, destroyed. So something like that. This same thing works in stock market also. Like if you put all your money in one stock, and that stock goes down, then you lose lot of money. So yeah, to particularly to avoid this particular situation, we come up with another solution. Let's you know use multiple location. Let's say in Bangalore location I put one block. In second Sydney location I put another block, and New York location I put another block of information. But the problem is this is not an ideal solution. The reason is because in this particular thing we need to use lot of network amount. There are lot of network bandwidth is going to use to access the data. Let's say if this got failed and I need this, then this is in Sydney, right? To access this particular information we need to lot of network bandwidth. And let's say if this got failed, then New York is very far from here, so like it's like huge network bandwidth is being used here. So balanced approach is basically is that we put uh, one data block in one location, and we put two data block in another location. So let's say we are using at one location we are using basically one block, and we now, if something happened here, we can access this particular information because Sydney is close to Bangalore basically. Because for that reason we have put on different racks also. Let's say this rack got destroyed, we have our data here. So basically this is like a more balanced approach, and that is how things needs to be stored. So yeah, this is all much about from my end of side today. Do tune in for more data engineering stuff, and if you are confused about any stuff, do comment out. I will be happy to reply and clear your doubt. So yeah, thank you. Have a nice day.